Okay, so here's an example problem. So let's say that this is 1 meter long. And let's say this angle is 60 degrees. And it makes frictionless contact up here with a wall where this angle is, let's make that 80 degrees. So there's no friction there. What are the reaction loads on the bar? Oh, and as the way I have it right there, the answer is 0. So let's put some weight in there. So let's say the mass is 100 kilograms. What are the reaction loads on the bar? Okay, so first, the way to go through all these problems is first draw the free body diagram, then translate that over to the table, and then go from the table to Newton's laws. So free body diagram. Where is the weight applied? I guess I don't think I said this explicitly, but when we were doing particle statics, it didn't matter where the weight was applied because everything was just at a single point. But now everything's at happening at a different location. It does matter where the weight's applied. So where are we going to apply the weight? Center of mass. Yep, that's right. Okay, so we have a downward force here. 100 kilograms times 9.81, so a force of 981 newtons. And now we're going to go around the boundary looking for places where the chosen object contacts things outside of its boundary. So one place is down here. This is a pin joint. So what load type am I going to apply here? Yep, total force vector. So I'll write that as RA. And then up here, that's a frictionless contact. So how am I going to treat that? That's a known direction, and so it's going to be perpendicular to something. What's it going to be perpendicular to? The bar or the wall? To the wall, yeah. So so it's going to be like this. I'll call this R, so I'll call this A, point B, point C. So this is a scalar that I'm calling RC. Why are you calling pin joint RA? Well, yeah, I guess you could also call it the force on the bar by the pin. That subscript notation, I guess, is helpful when you're going to isolate more than one object. We'll see how useful it is when we get into having like 4 bars connected to each other. But if the only things you're dealing with are like the ground and then the bar, and you're only going to isolate the bar, that subscript notation doesn't really help you. But yeah, you could always use it for sure. And what's the angle here? So if we're going to calculate the cosine and sine of this, yeah, so yeah, that's right. So if this was, is that right? Yeah, 170, right. If this was all the way, if this was all the way up, that would just be straight across at 180 degrees. We're 10 degrees short of that, so it's 10 degrees up that way. You can also use that idea where, so start at the positive x-axis, rotate 80 degrees, and now you're going this way. And now rotate another 90 degrees counterclockwise, and you're going this way. Okay. So now the table, pancake, artists, row 4, Mars. I try to keep saying that each time so you can't forget it when you're lying in bed. And where do you want to put the origin? I suppose sort of a natural place would be down here. So the force RA is acting at the origin, so P is 0. Now the about point. There's no right or wrong answer for where to put the about point, but you can simplify the math a little bit if you put it at a location where you have the most unknown forces. So like in this case, since we have 2 unknown forces, 2 unknown components at the origin, let's put the about point at the origin. Okay. So the row vector is 0 minus 0. The force vector is RAX, RAY, and take the cross product and you get 0 moment. And now we can go on to the weight force. What's the location of the weight force? Well, yeah, 0.25, 0.433, I think. So that's 0.5 is the distance from here to here. So it's 0.5 times cosine of 60, 0.5 sine of 60, and I think that's what that should be. The about point is still zeros. The row vector is 0.25, 0.433. The force vector is 0, negative 981. And the cross product is negative 245.2. Is that right? Okay, and then the last one is the force RC. Where's that acting? Yeah, so 1 times cosine of 60, 1 times sine of 60. So that's 0.5, 0.866. About point is 0. So the row vector is 0.5, 0.866. The force vector is RC times cosine of 170, RC times sine of 170. Can someone calculate those? Okay, so negative 0.985 RC, 0.174 RC. And then the cross product is 0.5 times 0.174 plus 0.866 times 0.985. Is that pi over 6? That's just an estimate. I have one here with all the answers, but then for some reason I always just like change the problems as I go. Okay. Yeah. Negative 0.68 RC. Okay, thanks. Oh, really? 0.94. Oh, it should be positive. Okay, so 0.94. Anyone else? Okay. Okay, positive 0.94. Okay, so Newton's second law says, so now we're just going to add all these up. RAX, RAY plus 0, negative 981 plus negative 0.985 RC, positive 0.174 RC is equal to zeros. And then the rotational equation says 0 minus 245.2 plus 0.94 RC is equal to 0. Okay, so you could solve for RC here, substitute it into the first one and calculate RAX, RAY. Or you could set it up as a system of equations where you have, so we have 0.94 RC is equal to 245.2. And then we have negative 0.985 RC plus RAX is equal to 0. And then the third equation is 0.174 RC plus RAY is equal to 981. Okay, so there's equation 1, equation 2, equation 3. You can write this as an augmented matrix now. So if you think of this row represents equation 1, equation 2, and equation 3. And then, so I'm just going to write it out like this. Okay, so this column represents our RCs. This is RAX. This is RAY. This one represents the constants that we've separated to the other side of the equation. So I'll call that B. Then what we have here is 0.94, 0, 0, 245.2. The second equation says negative 0.985, 1 RAX, 0 RAY is equal to 0. The third one says 0.174 plus 0 RAX plus 1 RAY is equal to 981. If you enter that matrix into your calculator, so name this M in your calculator, and then use the function RREF of M, it'll give you the matrix like this, and then your answers in the order RC, RAX, RAY in the last column. Did anyone solve that while I was talking? 935.61. Okay. Yeah. So for now, why would you ever use this method? It obviously takes longer, you know. It's a lot easier to use substitution for just these rigid body problems. But as the class goes on, we're going to have bigger and bigger systems of equations, and substitution ends up being pretty much impossible. And you're going to end up wanting to use this matrix method to solve these problems. So here's how you would solve it using the matrix approach. Okay, so these are the answers. So RC is equal to 260.85, and RA is equal to negative 256.94, 935.61. And these are all in newtons. Any questions? Yep. Yeah. So those point P's are just coordinates. So you're just trying to find the coordinates of this point and this point in your coordinate system. This is 60 degrees. The whole length is 1 meter, so to here is 0.5 meters. So the point B is 0.5 times cosine of 60 degrees, 0.5 sine of 60 degrees. And the point C is 1 times the cosine of 60 degrees, 1 times the sine of 60 degrees.
The one RAX was positive 256. I forgot.
Oh, okay, thanks. So this should be positive and this should be positive. That makes sense, yeah. Because the wall is pushing to the left on the member, so the hinge joint, the pin joint, has to push to the right on the member. Any questions about, other questions about that one? Okay, want to see something? It's not really about statics, but it's a useful thing in this class. It's going to be a useful thing in any mechanics class. Anytime you want to find the midpoint between two coordinates, so this is like an aside. To find the midpoint between points PA and PB, just average those two pairs of coordinates. So for example, from that last problem, our point A has coordinates of 0, 0, right? If you calculated the coordinates of the point C, that gives you 0.5, 0.866. So instead of using cosine and sine again to calculate the point B, you could just say that the point B is 0, 0 plus 0.5, 0.866 divided by 2, and it gives you the coordinates of the midpoint. Sort of a nice tool to have for, we're going to be doing a lot of geometrical stuff, and a lot of times, especially since the weight is always acting at the midpoint of members, this can often be a sort of a nice thing to have in mind. So let's say that a beam is attached to the wall. Let's say that this angle is 50 degrees. The length of this beam is 2.5 meters. The mass is 500 kilograms. And let's say that there also is a cable supporting a 200 kilogram mass over a pulley, where this is a right angle. And we want to know what are the reaction loads at the wall. Why don't you take 15 minutes or so and see what you can make out of this problem and work together on it. Let me know if you have questions. And feel free to talk out loud, whatever. You don't have to whisper. So after you have some time to work on that, I'll come back up here and do this problem.